If you were standing at arm's length from someone and both of you had 1% more electrons than protons, then the force of repulsion between you both would be enough to lift a weight equal to that of the entire Earth. Process that. You know, one thing I learned from reading books by scientists like Richard Feynman is the value of curiosity and the value of asking questions. And I think some of the biggest revolutions that have happened in science and in mathematics have come from people who have learned to ask questions. And they have learned to ask questions better than anyone else around them. And they've often placed immense value on mastering the fundamentals and challenging their own intuition for these ideas. So what I wanted to do was probably pick a topic every other week and then ask questions that a 6-year-old might ask. So today I thought I'll probably explore something that all of us think we know really, really well, and that is perhaps an atom. And we'll probably explore a bit about basics of electrodynamics. If you think about it, you've learned about the structure of an atom probably in high school, and then you've never gone back to think about it or to challenge your understanding of it. Most of us think we understand it pretty well, and then we close the books. So let's go down to that, right? So what do we really know about atoms? What do we know perhaps about charged particles? We know that there are protons, electrons, and neutrons inside the atom. But let's ask, for example, a basic question. What holds the electron together? The electron, clearly, we have defined something called the negative charge. And remember, that is completely arbitrary. There is no such thing distinctly as negative or positive charge. It's simply a label that scientists have given to sort of simplify the entire concept. But if there is a substance that the electron is made of, and if this substance is said to be negatively charged, then how come that substance is not flying apart into, different constituents? It's not exploding, even though it is made of a singular substance. So there's something that is holding perhaps the insides of the electron together. What is that? Or is it simply that the electron is indivisible by definition itself? And if then, how do you know something is purely indivisible? How can you say at this length, that is the smallest particle you will ever see? We can simply not break this particle apart. I mean, most scientists of the previous century thought the proton was indivisible. And today we know of all sorts of particles like quarks and leptons and all kinds of other particles. And they're clearly smaller constituents when compared to the proton, much, much smaller actually. The field of particle physics is so interesting because the particles that they study are so small that protons and atoms look like planets in comparison. So I was then thinking of a concept where we could dive into the atom itself, similar to how an astronaut would explore space, and an astronaut perhaps visiting the moon on his way is suspended in the middle of so much vacuum. And similarly, if you think about it, the atom is around 99.999% just space. So if we could only change the scale, if we could change our scale, and if we could shrink down into, say, a nanonaut or a Fermi knot, whichever the correct terminology would be, then we enter the atom. And now we can really test our intuition for it. What are you seeing when you look at an electron? Are you literally seeing a particle? But quantum mechanics tells us that it is a wave also. So are you seeing a wave? But what does it mean to see? To see means that a photon must hit the object and then enter your eye, right? But if the electron is so small, it is much smaller than a photon, then it cannot reflect a photon. Therefore, do you ever see an electron? No, you cannot by definition see an electron. There is no photon that can bounce off it. So if there is no way to see something at all, how do you begin to define it? That's the beauty of science. That's specifically when you're talking about things on a nano scale. It's this world where we as humans can see nothing. It is invisible to us. We are voyagers in a sea, and the entire ocean is invisible to us. And yet we are trying to describe it. We are trying to understand it. We are trying to understand its behavior. And I think that's beautiful. If you then say, well, what am I seeing when I see matter? I obviously cannot see electrons directly. What am I seeing then? And often you see the light that is emitted by an electron when it is excited and then de-excited, and then it emits a photon. But you never really see an electron directly. That's one thing. Another question to explore, perhaps, is what if you look at the nucleus, right? So the nucleus of the atom consists of protons and neutrons, which are held together by the nuclear forces. And as we know, the nuclear forces have a much shorter range, and this has important consequences. So if you take a uranium atom, for example, it's fairly unstable. So if you tap the uranium nucleus, which has around 92 protons, then it would divide, it would split into two parts, two different nuclei. And this is because of electrical repulsion taking over, because the nuclear forces are too short. So for such a large nuclei, the repulsion takes over. So the energy released in this splitting process then is the electrical energy. Even though we all call it nuclear energy is in fact electrical energy being released. So we should also be wary of some of the terminologies very popularly used in science, but it can actually be pretty misleading. And before I was talking about how an electron would look, or whether we would be able to see an electron. And this brings us to the concept of color. Does all notion of color disappear at the atomic level? Is color a phenomenon that only happens, after in the molecular level, after the molecules have begun to form? Is that the only time when we can have any relevance to the idea of color? Because if I am as small as a proton, as tiny, and if I'm inside the atom, would I be able to see the nucleus itself? I know the electron is way too small to see, but would I be able to see the nucleus? And if yes, what color would it be? Because color usually is not a property at the atomic level. We usually associate it with molecular level, because the material then has the properties of reflecting some wavelengths and absorbing some other wavelengths. But what color is a proton? What color is a neutron? Do these questions have any, do they make sense? Do they have any relevance? That's some stuff to think about. And I think even talking about charge, as we were before, when we define positively and negatively charged particles, have you ever thought about what makes them different? In the case of gravitational forces, you only have one kind of mass. It's mass itself, and everything has mass, and if it has mass, then it exerts and experiences gravitational forces. But in electromagnetic forces, you define two different kinds of matter itself. But why haven't scientists been able to explain what makes them different? In our textbooks, we never learn about what that intrinsic factor is that makes positive different from negative, right? Then we can go on to say, how real is an electric field? We are often introduced to fields as being very real. In the textbooks, we draw field lines emanating from, either magnetic poles or from electric charges. But how real are these? And I understand it is a mathematical concept, and it is used then for convenience in mathematical calculations. And even if you go down to read some really good textbooks, they will mention, in fact, that they will never be able to fully describe what a field is, but only what it is capable of doing. And they can describe the momentum of a field. But can you tell me what it really is? Probably not. We do know it takes finite time for a field to travel. So if I have one particle at the other end of the galaxy, then the field is going to take some finite amount of time. It is propagating at the speed of light itself, and then the other particle experiences the force. So we know that something is propagating through space. In the case of a photon itself, again, you have these oscillating fields of electric and magnetic waves. So if we do not understand what either electric field or magnetic field is, then understanding light is going to be quite complex. So these kind of questions really challenge me, because you think you know, and you think you're in college and you've got this all figured out, but really, what do you know? The question is not what you do not know, but what you do know, because what you do know is such a small circle floating in an ocean of the unknown. Well, I encourage you to post more questions like this, but I'm signing off, and I probably will ask more questions when I introduce more topics in the future. This is just a small sort of impromptu session, and I just wanted to play around with some of these topics. But see you in the next episode. Bye-bye.